Alright guys, let's discuss the Lrc circuit in series. So as we said, this circuit has a resistor, an inductor and a capacitor connected in series to a power source that is an AC power source. The voltage provided by the source changes with time as V naught cosine of omega t. So first thing to know is that the sum of the voltage through the resistor, inductor and capacitor should be equal to the voltage of the source. That's another way to write Kirchhoff's loop law. And in a series circuit, we have that the current through all the elements in the circuit is going to have to be the same. Conservation of charge means that this statement is true. So the current that goes through the capacitor equals the current that goes through the resistor equals the current that goes through the inductor, and that's equal to the current that goes through the source. So as before, we're going to call I naught the peak current in the circuit. So two questions, important questions to answer about this circuit is, the first question is, what is the equivalent impedance, reactance is another name for it, of this circuit? What is the equivalent impedance of this circuit? So that's the first question. The second question would be also very important, is how many degrees is the current in the circuit ahead or behind the voltage that it's applied to the circuit? These are the two main questions to answer when we're dealing with an AC circuit. So let's start with the first one. Now these two questions, mathematically speaking, mean that, well, we know that the current in the circuit is going to be a oscillatory function of time. It's going to be a cosine function. It's going to have a peak value of I naught, but the current is going to have some phase. It's not going to be directly cosine omega t like the voltage. It's going to have in general some kind of phase. So the first question, dealing with the impedance of the circuit, means that we're looking for this constant C, that if we write the peak current as the peak voltage divided by a constant, what is that constant? What is that value of the net impedance of the circuit? So we're looking for Z. First question is Z, the combined reactance of the circuit, also called impedance. When we have several elements connected in an AC circuit, we call the overall reactance, we call it impedance. So the first question means what is Z for an Lrc circuit in series? And the second question, from this equation, we see that we're looking for that phase difference between the voltage and the current in the circuit. So let me remind you what we discussed before. So when we have a resistor connected to an AC circuit, we found that the current phasor and the voltage phasors are parallel to each other. The voltage is simply in magnitude the current times the resistance. For an inductor connected to an AC circuit, we found that the current lags 90 degrees behind the voltage. So that means that in terms of phasors, the current phasor is going to be, we're going to draw the current in this circuit as a horizontal phasor. So if we draw the current as a horizontal vector, then the voltage in the inductor is going to be 90 degrees vertical, pointing up. For the capacitor, as we discussed before, if we draw the current also as a horizontal vector, then the voltage through the capacitor is going to be a vertical pointing down vector, as we see in the picture, because for a capacitor the current is 90 degrees ahead of the voltage. So with these three behaviors, we can find out what's the net behavior of the circuit. So since we know that the current, they share the same current, all the elements in the circuit have the same current, then we're going to put the three phasor diagrams that we just saw before on the same diagram. So the current is a horizontal phasor. The voltage in the resistor is going to point in the same direction as the current. For an inductor, we need to draw the inductor voltage 90 degrees with respect to the current, and we need to add in this diagram, this phasor diagram, we need to add the voltage of the capacitor 90 degrees but lagging behind the current. So the overall voltage of the inductor, capacitor and resistor is going to be the vector sum of those three vectors that you can see there, the blue, the green and the blue vector. So notice that the voltage of the inductor and the capacitor, you need to subtract them, and the net voltage is going to have a vertical component equal to the voltage of the inductor minus the voltage of the capacitor, and a horizontal component equal to the voltage of the resistor. So the net voltage of the three elements together is going to be the magnitude of that vector. The peak voltage of the inductor, resistor, and capacitor together is going to have a value of square root of voltage of the inductor minus voltage of the capacitor. Remember that the peak voltage of the inductor is the current, peak voltage times the reactance of the inductor, and the peak voltage of the capacitor is the peak current times the reactance of the capacitor. So we need to subtract those two, square it, and add to that the voltage of the resistor, which is simply the current times the resistance. Peak current times resistance gives you peak voltage in the resistor. So we take the square root of that, and that is going to give us the peak voltage of the inductor, resistor, and capacitor together, which should be equal to the peak voltage of the source, of the AC power source. If we pull out the current, the peak current from this diagram, I should write it I naught, since we said that I naught is the peak current. If we pull out the peak current out of this equation, then we can find out what's the impedance of the circuit. The impedance is defined as the peak voltage divided by the peak current. So clearly the symbol impedance is Z, so Z is going to be the square root of inductor reactance minus capacitor reactance square plus the resistance square root of that. Now this impedance of the circuit is a function of omega. Remember that the reactance of the capacitor and the inductor are functions of omega, which means that this function Z as a function of omega will have a minimum value. And from the argument of the square root, we can see that the minimum value as a function of omega would be when the inductor reactance is equal to the capacitor reactance. That gives one of the terms inside the square root 0, makes it equal to 0. So in that case, that occurs when omega L equals 1 over omega C. So that tells us that when the power source has a frequency omega, angular frequency omega, that is equal to the square root of 1 over LC, then we get what's called a resonance, because the impedance of the circuit is a minimum, which gives us the maximum current. So the maximum current in this circuit will flow when the angular frequency of the source matches what's called the natural frequency of the circuit. The natural frequency of an Lrc circuit in series is given by the square root of 1 over LC. This resonant behavior that we're finding here looks pretty much the same, or is the same principle as this resonant behavior that we discussed before when we talked about a system of a mass and a spring system. For the circuit that we have here, we have found that the current, the maximum peak current, happens when the frequency of the source, the applied source of voltage, matches the natural frequency of the circuit. For a mass spring system, which we considered before with damping, so it's like assume that we have a mass hanging from a spring, is immersed in some liquid, water, oil, or something like that, and we're going to drive this system. We consider this system has been driven, meaning that we can shake one end of the spring with a certain angular frequency omega. And for these kind of systems, in the first semester of introductory physics, we find that there is a resonance, that when the driving, the force that is pushing the system, when the driving's frequency matches the natural frequency of the system, then we get a resonance. The amplitude becomes very big. That natural frequency for a mass spring system is the square root of k over m. So when the driving is applied to at this particular angular frequency, we get the amplitude becoming large. So in the circuit that we have, the capacitor, inductor, and resistor, when the driving, in this case when the applied voltage, the AC source, has a frequency that matches the natural frequency of the LC circuit, then we have maximum current flowing in the circuit. Now the second question was about the phase angle between the current that is flowing in the circuit and the voltage. So how do we calculate this phase angle between those two quantities? So we know that the current and the voltage, the applied voltage, are not going to be in phase in this circuit. No, in general, it's not. They're not going to be in phase. There's going to be an angle between them. That's the angle that we're looking to calculate here. Now that angle is the same as the angle in this phasor diagram, where we have the voltage in the resistor in the horizontal axis, and we have the voltage of the inductor minus the voltage of the capacitor in the vertical, as the vertical component of the total voltage in the Lrc circuit. So clearly the angle that we're looking for is the tangent of the angle is the opposite divided by the adjacent. So the angle is going to be the inverse tangent of the opposite side, which is XL minus XC. We can cancel I because there's I in all components. So XL minus XC divided by the adjacent, which is the resistance of the resistor. So that's how we can calculate the angle alpha between the applied voltage and the current that flows in the circuit. That angle can be positive if the inductive reactance is bigger than the capacitive reactance in the circuit. So sort of like if the capacitor, the inductor is has a bigger reactance than the capacitor, then the overall behavior of the circuit is to be the behavior of an inductive. It's inductive in the sense that the current is going to lag behind the voltage. So that will happen when the inductive reactance is bigger than the capacitive reactance. Then the angle alpha can be negative. We call this a capacitive circuit, and that can happen if the inductive reactance is less than the capacitive reactance. So in that case, an alpha negative means that now the current is ahead of the voltage. So that reminds us of the behavior of a capacitor, where the current is ahead of the voltage. So we call this kind of situation a capacitive circuit. Alright, that's it for now. And the next video I'm going to discuss an Lrc circuit in parallel.